Catherine. I can't possibly live up to such a kind introduction, but it is a pleasure to be here. As Catherine said, I've been here since the beginning, since before this space was formed, and it's really an honor and a pleasure to be here speaking to you today. As Catherine mentioned, that's my hometown, which was a dangerous place when I was growing up, in Lattice QCD, which is kind of one of the dark corners of theoretical high-energy physics, and I did a postdoc on the development of numerical methods, and it was in this period that I really began getting involved with open source numerical tools for scientific research. I am today faculty in statistics. I just finished last week teaching kind of core lectures in bootstrap methods and hypothesis testing, but I come from a world of physics that carried this prejudice, unfortunately. And it is true that there's been a lot of training of scientists in the last few decades where statistical thinking has not been given the place it actually deserves in today's science. I am working to remedy that. So the next generation will learn better statistics. I promise you that. I'm working and I'm starting close to home. That's the stats classic that UC Berkeley is proud of for having created a huge amount of influence in the world of statistical thinking, and hopefully Lucia, my daughter, will one day. But I think it's important to discuss a little bit the motivation behind these ideas. And there are several, and I mentioned where I came from because it comes back to one of the axes that motivate me, which is an ethical one, which is the notion that building open tools is a fundamental piece of working fairly. And this is because, for me, even though I was doing a PhD in the US at an R1 university that obviously had access to whatever software tools I might need for my work, if I wanted to share any of the work that I was doing back with the people who trained me in Columbia, access to proprietary software licenses back in Columbia was not an easy thing, and it's something whose costs were very substantial relative to the economy of the country. So for me, trying to build my scientific career on open tools has an ethical dimension to it. One thing that I discovered quickly, which I wasn't fully expecting naively going into it, was the human and social dimension of sharing in the community that this built and became lifelong friends and partners and collaborators. There's also a very important point, which is the epistemological kind of line in the sand that I think we must draw, that if we consider that the part of the mission of scientific research is to, if you will, open the black box of nature and understand how it works, it's antithetical to that mission to perform that job with tools that themselves we are legally prevented from inspecting, right? Legally prevented under threat of lawsuit when you clicked on the little acceptance statement to install the software, that you will not ever try to inspect how it operates. And finally, there's a technical one, which was that, yes, I'm a geek and I like coding and I like computers, and Python at the time seemed like a breath of fresh air in the space of kind of computational tools that I had. Python, this is a slide from Carol Willing that comes from a quote from the creator of the Python programming language. The Python programming language was actually derived on teaching programming off of a language called ABC that wasn't as successful as Python, but ABC taught him some lessons. But he said part of the work that, the most important thing that Guido learned when he was at this research facility at the University of Amsterdam was not so much the technical stuff, but the value of sharing and collaborating in an open community, and that has permeated how the Python community itself works, and that's a lot of what drew me really actively into and very energetically into it when I began doing it. And the second part of another idea that goes all the way back to Guido, but that I think all of the work that we have done with these tools actually kind of continues in that lineage, is the notion that programming languages are really languages also in the human sense. They are tools to express ideas, to reason, and that they are tools really to communicate among human beings. We actually express ideas for each other with code. And yes, the computer is one of the partners we've built, because what we have are tools really for the humans. Everything that I will be talking about today, even though it is in the context of complex scientific questions and where algorithms matter and data visualization matters and analysis matters and performance matters and accuracy matters, our realm is that tries to build tools for the limited brain bucket that we all have that isn't getting any bigger, any faster. And whether your computational environment is a small laptop or a really large machine, this part will remain what it is. It won't scale, it won't get any faster. And so what we're trying to build is a layer precisely between the humans and the computation for that conversation that happens where the computer is a partner in the computational dialogue, and where humans are themselves in dialogue using the computational tools, very much in the spirit of what Guido said. So as Catherine was mentioning, all of this began back in 2001. This is actually the original implementation of IPython. Is about almost 20 years later, and we're still working on it. So obviously my ability to estimate anything, that's about as good as my error bars are in home renovation projects and home fixing things. But at the beginning, it was a tool really to try to give myself, in my own analysis workflow, interactivity, the ability to run a small snippet of code, see the results of the code, plot some of the data, keep iterating in this process, which is a little bit different from the process of building software as a software engineer, right? It's the process of using the computer to think about a problem, to iterate something which is very natural to all of us in science, but which is distinct from how a lot of software systems are built for the development of large-scale computational systems. And this exploratory nature of the project has driven what is now an amazing team. Many of you are here in the room, and it's them who deserve all the credit for everything we'll be talking about today. So these are a couple of pictures from two of our here. That is a great little conference venue. And one of the interesting points is that there are people here who come from Berkeley. There are people who come from national labs like LBL. There are folks there from industry. There are folks from a variety of communities. And this is a project kind of draws from all of those sources. And that is, I believe, one of our strengths. And in addition, last I counted, and I did a quick check on GitHub, I think a rough tally is that we've probably had about 1,500 people in one way or another contributing to the source code of the various pieces that make up kind of this ecosystem of Jupyter. So it really has become now a large collaboration, and they are the ones who deserve all the credit. Very quickly, from that terminal-based environment that I started with in 2010, if we jump a little bit more than a decade to today, one of the key pieces of the system today is something that we call the Jupyter Notebook. It used to be called the IPython Notebook, and I'll get to that transition in a minute. For those of you who have web-based interface that allows you to build documents, those documents can contain text, including mathematics, and this is important from the beginning to have good mathematical notation. But in addition to text, they can have computer code, and there can be output from that code. And all of that, the combination of text, computer code, and the output of the code is stored in a document format that you can share, that you can turn into other formats. And the fact that it's accessible through the web browser is an important architectural decision that we'll get back to in a minute. And so in order to think about kind of what are the basic building blocks of the system in terms of ideas, if you ignore for a moment the specifics of how things may be implemented on any given day, the core ideas of what we built with Jupyter are probably easiest to reason about if you think about the web. So the web is built in a simplified fashion, and this is not a CS network protocols presentation, but in a very simplified fashion. The web is built around a protocol, the HTTP protocol, that allows, the point is that by virtue of this being a standardized protocol, you can actually connect other clients to servers that speak the protocol, and you can build applications that may not necessarily be using web browsers, even if this is the most common one. And on top of that protocol, that's low-level way of speaking between parties in the process, if you want to encode that content for its delivery as a human consumption, as a humanly consumable rendered page, you encode that specifically in HTML, right? But you can send non-HTML data over the wire, and you can have clients that are not necessarily rendering documents. Fairly similarly, what we've ended up doing is building these ideas of interactive computing that began all the way back at the terminal. Right, we actually sat down and went through the process of asking, okay, let's just make a list on a piece of paper. What do we do when we work interactively? These are the things we do. These are the actions. What is the communication pattern? What kind of data flows back and forth? We wrote all of that down. We documented it. Chose, because it is very low level, very fairly high performance, actually quite high performance, and implemented in C++, which means that it has bindings, or you can write bindings for it in just about any other programming language, which means it was a good building block at the bottom. And the data that is sent over the protocols and the specifics of the connection, you can ask me about it later if you're interested. It doesn't really matter right now. The data is JSON, JavaScript Object Notation. This is, again, a very widely available way of encoding data that many programming languages know how to use. Virtually today, any language worth its salt will have a JSON encoding and decoding library. And if it doesn't have 0MQ bindings, you can build them for it because it's really clean, compact, lightweight C++. And so on top of that protocol for how the pieces would communicate with one another, we built a format. We designed a format that is basically capturing that traffic into something that can look like a document, which when you do have a document, when it makes sense to have a document, then you can render it. And we'll get back imagining that process of computing interactively, reimagining it for the age of the web. So instead of simply capturing the output that you could print at a terminal, we said, well, what can you return? You can return text, but you could return images, you could return mathematical objects, you could return formatted HTML, you could even return live interactive controls that maintain a communication between the rendered object and the code that is executing. So this is an example of writing a function that will expand and factor the polynomial x to the n minus 1 symbolically, and gives you a little controller to explore what that looks like, what the factorization of that polynomial looks like, but writing one line of code. The only thing you do is you write interact. That's it. So the idea is, how can you as a scientist get a little bit of interactive exploration without becoming a graphical user interface designer, which is something that is quite time-consuming and difficult to do. All of these things are part of the process of exploring the idea that you could have different clients, you could have different servers. If everybody is compliant with the protocol, you have a system that can grow. It was called IPython, but quickly we were able to invite, actually in summer of 2013, we had the team who created the Julia programming language. They visited us for a few days, and they built support to compute exactly using the same machinery, but instead of Python, to do it in Julia. No Python in the picture, completely different programming language. Obviously, building that showed a bunch of misconceptions and lacks of ambiguity in the protocol specification and whatnot that we had to kind of iron out all those kinks. But after doing that, we did R. One of a former postdoc of mine at a meeting actually organized by Karthik at GitHub did the first prototype of an R implementation. And once you do this a couple of times, you've basically done the generalization process. Once you go from one language to two, then to three, you've pretty much worked out most of the kinks and the things where community by now has implemented support for these things in a variety of languages. There's about 100 of these right now, give or take. Of course, some of them are toy projects, some of them are kind of weekend demos, but many of them are actually serious tools that implement this machinery for completely different programming languages, including something like interactive C++. Turns out that you can use C++ as an interactive language. This was a tweet that just came out a few days ago. It turns out that there's a SparkQL kernel that lets you operate, and I think UV must have had a part in the construction of this, lets you operate on Wikipedia data, directly query Wikidata, and I think this is actually hosted on Wikidata. So this is kind of what happened as we built this architecture that began to grow in computation. But what happened was, in the building of all of this, we began developing an environment that gradually became a little bit of a Frankenstein. So we called it the notebook. You need to install something. You need to access a real text editor. So all of a sudden, you're adding a terminal to this thing. And next thing you know, you want a nicer text editor because not everybody's happy using VI or Emacs. So all of a sudden, the notebook application had all of these other components, and there's more pieces to it that had been kind of glued to it in a very Frankenstein style. So over the last few years, in close collaboration with Bloomberg and Anaconda, we've been building effectively a reimagining of these ideas into an application called, I would say an architecture called Jupyter Lab, which is a system that provides the same user-facing functionality that we had before with a much more flexible user interface, but more importantly, that expresses all these ideas as actual individual components that can be recombined in novel ways, where the scientific community can hopefully build other things, and where completely new systems can be designed that may not even necessarily an actual live demo. And we'll see how this goes. So this is what Jupyter Labs looks like when you open it. For those of you who have seen some of the modern wave of text editors like Visual Studio Code, it's not that dissimilar. You have panels on the left that expose things like what is currently running, what files do I have access to, what commands are available. This is actually an extensible system. And here you can create new notebooks. In this case, I have Python, Julia, R, and a few other things installed, as well as a few other things that we'll see in a minute. For those of you who are not familiar with the kinds of things that IPython can do, it may be useful also to see. This is a notebook, and for demonstration purposes, we can make it kind of be the only thing on the screen. And this is the kind of things that IPython does. You can put code in there. You can load a data set. Let's imagine that we want to try to model that data. It looks like it has some oscillatory behavior. I don't know where it came from. This is my job. And so I'm going to try to imagine how could I possibly model this data set using the tools available to me. If I think that I might have a little bit of some linear behavior, it's always a good start. There seems to be a pattern here that is nonlinear, and there's some oscillatory behavior, but with a non-constant frequency. So a very simplistic guess for that data could be something like this: a linear term, a quadratic term, and a sine x squared term. That's a good start. But maybe Python isn't enough to solve this problem. So we can ask the Julia programming language to help us in here. So in here, I've defined a function to compute x squared, because Python doesn't know how to compute x squared. So we're going to do that in Julia. So now we have a function created in Julia. This is the Julia syntax for x squared. And now I can ask to compute. It has the same shape of my data, so Julia didn't make a mess. For the next feature, which is horribly complicated, maybe these tools are not enough, so we need the old workhorse of science, which is Fortran. Fantastic language. In some ways, it has not been bested by anything yet. So we're gonna actually use Fortran as if it was a scripting language. So we pull in Fortran, and we define here a function, sine x2, which will compute the sine of x squared, because neither Julia nor Python are capable of doing that. So now we have our next feature computed in Fortran, and this is all in the same process with the same data in memory. And now we want to try to actually build a statistical model for this, but neither Python nor Julia know how to do statistics. This is the job of R, so we ask R to help us. So we put our three features into a little matrix. We have X, F2, and F3, our three little features. And we say, okay, R, could you please try to build a linear model for that design matrix and output? So what this is telling, what this line is saying is, the next block of code is not going to be in Python. It's going to be in R. It's going to take Y and A, my data, my observations Y and my design matrix A as inputs. And when it's done, it's going to give me the fit coefficients back as an output, right? And R comes to the rescue, and it does the fit. And those of you will recognize these as the standard diagnostics plots of a linear model in R. And so, but R is absolutely terrible for looking at results. So those plots are not what we want. And so now we need to get back to Python to finish the job and see how our model worked. So we have our fit coefficients that were computed in R. They're a vector that has those three values. So since we built the linear model, if we take this product, we'll now have our fitted model, and we see an actual result that was computed by having Fortran, Julia, R, and Python collaborating in memory, operating on the same data, each of which doing a piece of the job. Of course, you could do all this in any minutes to demo. They do have different strengths, and we've built machinery to help them collaborate and cooperate and bring each what you may need from any of them to the table. And we have polyglot data science. There's other tools. For example, Cython is this kind of happy child of, well, happy or unhappy depending on your flavor of languages. Sometimes it is a little tricky to reason about, but in many cases an extremely powerful blend of Python and C. And it's something that allows you to do things like the following. Let's say that you want to write this code. This is a very straightforward numerical integrator in Python. If you load the Cython support, you can copy this same exact code and simply annotate with type information. The actual code, if you notice, the actual code hasn't changed at all, and the code down here is exactly the same code that we had down here. We're just adding type information, and what Cython does is it converts that code with the XU. The more yellow, the more code it had to generate, so there's potentially more hotspots in there, and you can basically study what did it do as it generated C to try to help me. And this is a comparison of running a timing comparison of the Cythonized version of the Python version. Remember, we didn't have to change the code at all. We just annotated it, and it's 100 times faster. So this is the kind of thing that can potentially make the difference. A factor of 100, by the way, that's really the difference between something being viable and something not being viable, right? This isn't simply go to lunch. That's the difference between a project finishes and doesn't finish. And there's more here that I can show you later about kind of the interoperability between these tools. But the point is, even IPython, this is not Jupyter or JupyterLab, this is the core of IPython, is a tool that was designed for kind of modern, interactive, exploratory data science with all the tools at our disposal, not just the Python machinery. But in addition to these tools, so this is what notebooks look like. You can have a native R notebook. This is an example of opening a notebook that was actually in pure R. If I try to load matplotlib into it, that doesn't work like that because import is not an R statement. But if I run my traditional R code with ggplot, you get standard R code. So the point is, you can either run natively in Python with all of this language interoperability, or you can install other kernels that will run in other programming languages. Let me get back out of single document mode. And oops, I think that's So one of the things that the user interface allows you to do now is to have more than one document in the same environment. And in addition, very handy if you're not on a tiny laptop and you're not zoomed into death and you're actually working on a remote server where you're doing a ton of data analysis, beginning to be able to bring these tools together in the same environment helps a lot. You have this as a normal terminal. You can run whatever you want in it. But in addition to notebooks, it turns out that we do have now support with this architecture for things that go beyond notebooks. So let's imagine that you have a markdown file. So let me close this terminal right here. Let's imagine that we have a markdown file. We can ask for we can preview this markdown file live, but more importantly, because this is something that just about every text editor has, the point of our architecture is to allow you to combine these things with computation. So maybe you don't need a notebook. Maybe you're writing matched to this document, and now when you have a block of code, if you hit a keystroke, now that block of code goes to what's called a console. So a console is something that reuses the same machinery of notebooks, but is not itself a document. It's simply the underlying computational process and the representation of the output, so that now you can say, okay, as I'm building my document, I need to execute some code. I need to validate that the figures for my paper are what I need them to do, but I'm not in a notebook-based environment. I'm writing, say, a tech or markdown-based document. This is now kind of decomposing the pieces of the system in a way that allows you to reuse them in a different way. In this case, consoles, text editors, and documents kind of weaving computation in a completely different form. And in addition to computation and documents, the other piece of this process is typically data, right? And so we have data types, such as bread and butter of a lot of people's lives. We have built proper CSV viewers into the system that allow you to view common data types, such as a CSV file. This is an example of a CSV file that takes a little bit longer to open. This CSV file, let me scroll down to the bottom, has 1.2 million rows. And that's how long it took to open, and that's how smoothly it scrolls. Don't try to open this thing in Excel. It will not be happy. Those of you who have tried to open 1 million row tables in Excel know that Excel is not a happy camper when you feed it that much. So this is partly also to show that all of the components of this have also been designed for performance. So yes, human exploration is important, but performance has been a consideration. So large-scale data works fairly well. The system supports things like images. One of the most common data types today for encoding information is this. So this particular data file is actually a schema that encodes geographical information, in this case, museums and DC. So what we've made it is very easy for you to build viewers that recognize specific data types and will represent them using the capabilities of the system. So those of you who do genomics will recognize FASTA files as long lists of A, G, C, and Ts. This is one of the standard formats in genomics. This is in particular multiple assemblies of the Zika genome. And if we open it in this format, it's much easier to see where are there differences in the assembly. So this is a FASTA viewer that we didn't build, but someone basically adapted it to the display protocols of the system so that if this is the kind of data that makes sense in your workflow, now it's very easy to access it using the system. And to close the loop, I want to show you one last thing with this, which is, okay, now that we have that FASTA viewer, this is the tiny document in a notebook or in one of the standard workflow tools, so that you don't have, oh, well, somebody built a viewer over here, but what if I need to write a loop over files? What if I need to have some code? I don't need to be clicking on files. How can I use that as code? Because they are the same abstractions, because they have been decomposed in reusable little blocks, you can say, okay, with that little bit of code, now that viewer that was over here becomes usable as a normal programmatic piece of a library. And basically, the actual code is this much. It's basically 2 lines of actual code. It's encoding a teeny little bit into the right JSON spec. The rest of it was just opening the file. That's it, just reading the data. So very small amounts of work illustrate kind of how you can compose the Lego blocks of the system, if you will, to build the tools that make sense to your workflow. And before we go back to the slides, I want to close with a different system. So this is an example of a Markdown file. This Markdown file, if we view it, looks like this, just a very simple Markdown file. And at the bottom, it's in lowercase. If I go back here, it turns out that this is calling lower. Let's say that we call upper. Now it's in uppercase. So what we have here is a Markdown file that when loaded by this little bit of code becomes a live, in this case it's using React, it basically becomes a live user interface. Let me kill this one. You can do more complicated things, such as loading kind of a more complex file that includes things like, oh, sliders for plots, so that as you change them, code is being generated. A table, for example, a table built nicely with React, which as you fill the data frame, it's constructing the data frame, but it's updating the view. This is purely Markdown, but you have a live responsive interface, and the person who created this that is the right architecture for representing computational processes and interfaces, but I don't need what they've built. I don't need the UI. I'm not interested in notebooks. What my team needs is an easy way of creating documents that expose the computational process as a nice reactive interface with minimal effort. All they're going to know is Markdown. How can I get that? And so he took the pieces of the JavaScript libraries that expose all these primitives and reassembled them into a brand new server where you don't see any of the user interface whatsoever, and yet he was able to do that with a minimal amount of code. And this makes us really excited because it's not only the fact that the system is extensible. The JSON extension was something. The GeoJSON extension was made by someone else. The FASTA viewer was made by someone else. There's many more. It's not just that. It's the fact that the entire architecture itself can be used to build new computational workflows that we use the same primitives. And we've put a lot of effort into that. And as I said, the credit on all these things goes to other people, not to me. So after that bit of demo, of these ideas, so this is a quote that I've used in many, many talks and in my class last semester. Many of you I know here are familiar with that quote, but for those of you who aren't, it is something that I strongly subscribe to. It was something that Buchheit and Donahoe said back over 20 years ago, paraphrasing John Claerbout at Stanford. And so the question is, well, if we believe in this idea, can we build tools to support this vision of research? And I would argue that we're at least on our way to doing so. So this is an example of a paper that was published in 2016 by 2 researchers in Norway who are analyzing wind patterns in Europe. And we're doing a statistical analysis of wind patterns in Europe with about 100 years of data. And they published, in addition to this paper, they published a GitHub repository that contained their data and notebooks and the code behind the analysis. So this is what their paper looks like. This is a screenshot of the PDF of the actual paper. I just went out, downloaded the paper. And these are screenshots of the notebooks on GitHub. I'm going to give you the whole thing that actually created the publication so that you can validate it, including the data. And it turns out in the fall I was teaching a course called Reproducible and Collaborative Data Science. So I figured, okay, what better exercise to get the class going than to have them replicate this? The authors made the code available. They made the data available. It's all using Jupyter. It's all fairly recent Python. Go ahead and do it. And of course they couldn't do it. not because of their fault, but because something had changed, something had broken immediately. Even in the authors with the best intentions, and little things had changed, and the students immediately ran into small issues. But it was a really interesting experience, because what happened was, over the process of the students working on it and us analyzing it, it led to Thomas Caswell, who is the lead developer of Matplotlib. He was visiting here, and I showed him one of the weird things that we had found, this very bizarre change in one of the figures, and he said, aha, I know what happened. He did something that he's effectively misusing slightly version change in Matplotlib, but he went ahead and actually, the lead developer of Matplotlib made a pull request against the repository of the original author of the paper, and I similarly made another one to kind of improve a little bit the reproducibility, and the author very kindly responded to us saying, thank you for doing this, and actually updated his work. This was a great experience in teaching this to the students, because they actually were working on this process, and they saw a back and forth between what they were doing and the authors of the publication that led to an update in the code behind the paper. So I think this is one small bit of evidence that shows that we are on our way towards that. In addition to the machinery we've been talking about, there's kind of another layer. Once you begin talking about teaching large courses and doing things at scale, there's another piece that comes into the picture, and it's a tool called Jupyter Hub. It's part of the project, and it's a system that enables you to deploy these resources in organizations where you now have authentication, you have multiple users, you want them to, the Jupyter, the Python, the R, the Julia, et cetera, machinery that we've been talking about, but in a hosted environment. And so it means that you can share hardware, you can share data storage, you can share the work environments, you can share the workflows between people. So it becomes a platform for collaboration that can potentially have impact in science and education. So for example, our colleagues out at NERSC up the hill actually have a Jupyter Hub deployed on that Cori machine. So Shreya's here in the room, and his colleagues have actually worked on deploying this to access. This is one of the nation's fastest supercomputers. You can also connect this to web-based content. And putting those ideas together over the last few years, we've been working on something that began as a conversation with Jeremy Freeman, a neuroscientist who used to be at Janelia Farm, the Howard Hughes Medical Institute, but who is now at the Chan Zuckerberg Initiative here in Palo Alto. And it's something that is called Binder, and the Jupyter machinery, content hosted on GitHub repository, so that you have all the code available for executing an analysis. And very importantly, you said explicitly what are the dependencies to run that code, right? Because typically in a repository, you don't put every library you're ever going to use in your repo. You say, I'm going to need this and this and that in order to run this. So if you make that explicit, precise, and machine readable, and then you add a little bit of magic cloud pixie dust in the form of Docker containers and Kubernetes deployed machinery, then what you can have is the union of these things can provide a shareable unit that is now not just notebooks, not just code. It's the full environment represented in a way that is executable. That's what a Docker container gives you, and actually with machinery to deploy it quickly and easily in a repeatable fashion in the cloud via Kubernetes. And so the Binder, what the user sees, and as long as it follows the convention of declaring what it has, you can optionally choose which branch you want. You click a button, and I will go, I being Binder, I will go assemble all this and give you back a link that lets you run that code. So it's basically enabling someone who follows the right practices to, with one link and one click of a button, create a completely portable, reproducible environment that can be given to anyone else to share, so that now, once you have these things, you have completely on-demand environments that are customized with the computation, the code, potentially the data, either if it fits or if it's accessible via the cloud, to replicate end-to-end analyses. This actually has been used, so some of you may have noticed that last year there was a Nobel Prize was awarded in physics for the discovery, the observation of gravitational waves. This was a prediction made by Einstein about 100 years ago. The field equations of general relativity actually, in the way that charges radiate energy in the form of light, they would radiate it in the form of a wave that travels at the same speed as light does because of that factor C in there, but it's not the oscillation of an electromagnetic field like this laser, for example, or the photons coming from these lamps. It's an oscillation in space and time itself, right? So this was a theoretical prediction that Einstein made about 100 years ago. Turns out that oscillation is extremely tricky to detect. That oscillation is a perturbation in space and time of the order of 1 part in 10 to the 21. So this is a devilishly hard problem. If you think about it from a sensitivity perspective, that's roughly the imaging equivalent of looking for an object of about the size of a human being, like a meter-sized object, in an image that is not an image of, say, a city, or even an image of a country, or even an image of a planet, but an image of the entire Milky Way galaxy. That's what 21 orders of magnitude looks like. So it's a very, very hard problem at Gravitational Wave Observatory. One is in Washington, one is in Louisiana, and these things are 4-kilometer long tubes at 90-degree angles. You shine a laser back and forth down these tunnels with mirrors at the end. And as light bounces back and forth, because it's laser light, so all the waves go up and down in sync, as long as everything is quiet, nothing much happens. If a wave goes by and space-time itself stretches a little bit, one of the arms is going to go longer than the other, and you're going to detect an interference pattern in the light, and it's extremely sensitive. With a mountain of both engineering and statistical data analysis, 30 years worth of work, you get to this. So in September 14, 2015, they detected the merger of 2 black holes that were about 30 solar masses total, about 1.3 billion light years away from Earth. And as they spiraled into each other, they produced a vibration that looked like this. These are the 2 signals. So this is roughly kind of like that sine squared thing that we started with. So it's a signal whose frequency increases in time. This is the first figure in the main paper of the LIGO discovery that led to the Nobel Prize. It's probably going to be one of the most cited papers in physics for the next few decades. And it's really interesting to notice that NumPy, SciPy, Matplotlib, the color maps that were developed here at BIDS by Stefan van der Walt and Nathaniel Smith, all of these open source tools are at the heart of this analysis. So all of this was done with these tools built by an open collaboration, and the LIGO Center actually made the entire analysis available to the public as in the form of notebooks. Did you hear the little chirp at the end? So that, whoop, that is the sound of 2 black holes merging 1.3 billion light years away. The sonification of the data. But it is real. And you on that link, and you can either run on Binder, the version we host, or actually they have an equivalent copy hosted on Microsoft Azure's notebook servers. So this project continues to grow. We have funding from the Gordon and Betty Moore Foundation. We're exploring how it's going to continue growing. But all of this is leading to the fact that these tools are now not just tools for research, but they're becoming tools of research. So there's now over 1 million notebooks hosted on GitHub, and a UCSD researcher recently downloaded all of that data, made it available to the public, and actually published an analysis of what are the practices that scientists follow as they do this kind of scientific research using these platforms. So if anyone is interested in these data, the links are there so that you can actually grab the data sets yourselves and do your own analysis. I think there's a lot of interesting work to be done here. And then after this, I'd like to talk a little bit about education. As Catherine mentioned, I am here now. An important part of my job is teaching in Berkeley and upper division courses in data science at UC Berkeley. And these courses have been written, they're publicly available on GitHub. They have been written actually as collections of notebooks that have a button up there, which if you click that button, then it takes you as a student, or as anyone, any of you with a Berkeley AD, you can click on that, and it takes you to a hosted version where you can execute the textbook live. This is hosted on something called the Berkeley Data Hub, which is basically a combination of Jupyter Hub plus the content from these courses that has been developed by Berkeley faculty, and it's supporting right now upwards of 2,500 users. These courses are really, really big. So these are pictures of Data 8, Ani Adhikari teaching Data 8 and me teaching Data 100 this semester. That's Wheeler Hall. That's the biggest lecture hall on campus. And it's now basically packed to the gills. These are the fastest growing courses in the history of UC Berkeley. This is the enrollment of Data 8, which is Data 100, and they continue growing. This is turning Berkeley into a place which in a few years, basically asking someone whether they know how to do data analysis with these tools is going to be like asking them, do you know how to use email, right? We're kind of moving the baseline of what does it mean to use computational tools. We have one of our BIDS fellows, Sierra. I don't know if Sierra is in the room. I'm sorry that I didn't check with you if I could use your quote, but it's only a minimal part of an email where she said she had a really interesting analysis of what she is observing here at Berkeley when she tries to hire students. Even looking 2 years ago and now, she's saying that she's really noticing an amazing shift. There's kind of a transition happening with the level of expertise that the undergrads that she's trying to hire bring to her work. And this is a message from this morning, so if you haven't checked email today, you haven't seen it yet, but this was in your inboxes for those of you who are at Berkeley, where the chancellor announced that now been working with a team of people for the last few years very, very hard on making this happen. I think they deserve a round of applause because this is amazing. And we very much look forward to teaching all of these students. We still have a lot of work to do, but it really is it's an exciting moment. I couldn't have asked for better timing for this email to come, to have a chance to kind of thank you guys and acknowledge you by doing this. We're not the only ones doing good work, though. Canada, for example, is a country that is now deploying national supercomputing infrastructure using Jupyter for the whole country of Canada. So they have central, nationally hosted infrastructure. They're deploying, they have a project called Syzygy that allows you to access Jupyter anywhere if you're a Canadian researcher. They're also, the same team is collaborating with a different sub-project on deploying these tools for K through 12 education. So they're literally covering from kindergarten to supercomputing across Canada. They are being adopted fairly widely in industry. This is a snapshot of some of the companies. You may recognize some of the small players in there. But there's also some newcomers, such as CoCalc and CodeOcean and others, who are deploying, sort of using these open source tools to build commercial infrastructure. And some of these we have partnerships and collaboration with. They're welcome to use the source code, but some of them actually find it productive to contribute and work with us. If you're interested in some more of this, we actually have now an annual conference. It'll be in August, the first week of classes, very conveniently timed for those of us who teach. The first week of classes in New York this fall. The last edition was a blast. We had a great time. It was a really interesting conference. So please come. And I'm going to close by mentioning something that I know some of you may have seen. It's been generating a lot of traffic on Twitter. It was an article written in The Atlantic about scientific communications, and it talks about Jupyter and other commercial tools in this space. It turns out that I think, I'm not going to get into a lot of the specifics, so some of these tools that are not open are declining in popularity, and I think there's good reasons for that. It's also interesting to notice this is a Google Trends data set for IPython, Jupyter, and Mathematica search terms, and you can see the where the lines are going. An interesting point from these lines is that there's a seasonality here that you can see in the Mathematica data, which is expected because it's a very widely used tool in education. And so as the semester cycles go, it dips. So it dips in December and it dips in July, right? And the dip in December is narrow, and the dip in the summer is broad. So it completely matches the notion that it's winter break and summer break, right? What's interesting is we're beginning to see those dips now in Jupyter, and we were not seeing them earlier. So it's interesting to see the appearance of the educational usage. At the earlier the data didn't have that much of a pattern. It was basically researchers, hobbyists, programmers, etc., with no specific educational calendar attached to it, where we're seeing educational use. So it's kind of interest. But to kind of close the loop with these ideas and to embarrass Catherine back, I really do think that these two quotes capture sort of what it is that we're doing differently. So these commercial tools that these authors talk about are actually very valuable, and they're technically very, very solid tools, and we completely recognize their importance, but we do have a different both community and ethical and scientific perspective on what it is that we're doing, and I think that's what brings it value. And I'm going to close by thanking everyone here at Berkeley, because this is an international collaboration. The team that is represented, that I presented earlier, has people from all over the world. But it turns out that Berkeley has actually played an important role in this project. There's a number of people here, past, present, future. Lindsay is a Canadian postdoc from UBC who will be coming in a few months. Jason Grout is not a Berkeley person, but he's kind of an honorary bit. Has been an amazing place to do this. I couldn't have done, I'm sure that none of this would be where it is today if I didn't have the opportunities and the colleagues that I have here. And so I want to thank you all. Acknowledge also the fact that we've been supported by the same people who pay the bills for this place, also pay the bills for a lot of this. So when you do see your friendly program officers, remember to thank them. And thanks to all of you. If you have any questions, I'd be happy to chat.
Thank you. So I think you got Fernando's plans for World